Hi, we learned the fundamentals of masking. Again, what is masking? Masking is phenomenon of reduced sensitivity to detect the sound, the target sound, when another sound is going on, which is masker. When the masker is present, then it influences the ability to detect the target sound. That is masking. So, for example, if the target sound to detect is this tone, and the background is masker like this, then if we try to listen to detect its target in the background, then it's like this. So it becomes harder. Or another example, if the background, masker background is also another tone in different frequency like this, then the situation is like this. The masker and the target. Okay, so in either case, masker makes the target sound less detectable. So in this example, masker and target are going on at the same time, so we call it simultaneous masking. Then another situation going on here we need to study is masking called non-simultaneous masking. So as the name says, it is masking when masker and the target are not in the same time, not occurring in the same time. So it's like this. If you look at this picture, it's like this. So look at slide 19. So there are two types of non-simultaneous masking. One is forward masking, the other one is backward masking. As you can see, in forward masking, masker is played and then it turned off, and with a little bit of time gap, the target is played and we are trying to detect the target. Backward masking is the opposite. The target is present, target is played first, and then a very short target, and then it's off, and then with time gap, background, the masker is played on. So the backward masking is may not be really entirely intuitive. It doesn't make sense, but let's get back to this later. Let's first focus on forward masking. So masker is played, turned off, and target is going on. The first thought you may have about non-simultaneous masking may be this: wait a minute, masker and target are not going on at the same time frame, and how can the masker have an impact our ability to detect the target? It does not make sense. That may be your first thought, which is perfectly fine. Good question. I can say this. First of all, the time gap we are talking about between the masker and target is pretty short, about 100 milliseconds, which is 1/10 of a second or even shorter. So first of all, we are not talking about time gap of a few seconds delay between the masker and target, which is really obviously separated in time. We are not talking about that, but we are more talking about the situation where masker and target are pretty close in time, but still separated about that short period of time. So my answer is it could have an impact. It could have an impact if the delay, time gap is short enough. And what exactly is going on here? How can this happen? The answer is because of some lingering effect in the nerve activity in the auditory system. Whenever sound is going on, we know that the sound is converted into neural signal, which is basically electrical signal in the auditory system, going all the way to the brain. So what's going on here is even when the masker, even when the sound is turned off, the neural effect may still linger just a little longer, like a few, like a little bit, 1/10 of a second, up to 1/10 of a second, something like that. So there's some neural effect going on. So because of that neural effect, which is lingering effect, that may have an impact for us to detect the target sound when the target sound goes on right that time period. Then the next question is, how long should this gap be? Should this delay between masker and target be to have masking effect? The answer, short answer is the shorter the gap, the more the masking. So if the gap is 100 milliseconds or greater, then there will be hardly any effect. If the gap is less than, say, 50 milliseconds, 20 milliseconds, or 10 milliseconds, which is pretty short, or even just a few milliseconds, then we expect a lot of masking effect. So that's short answer. For the same delay, the next thing you can consider is, next factor is for the same gap, the louder the masker, or so the more intense, the greater the intensity of the masker, the more effect of masking, which is also which makes sense, because obviously the louder the masker is, the more masking effect you would expect. So that's another thing. Finally, the same rules apply as we had in simultaneous masking. When the masker and target are closer in frequency, then we would expect more masking. The same thing applies here. If the masker is tone or narrowband noise, then the closer the masker frequency is to the target tone, then we expect more masking. By the way, why do we study non-simultaneous masking? So what do we learn? What do we gain from studying forward masking or backward masking? The first answer is for forward masking. As we consider the basis of forward masking, which is neural behaviors, neural characteristics of the lingering effect of the neurons, forward masking allows us to study, allows us to understand how neural behaviors really work. So that is one answer. Another answer is as you study forward masking patterns, the characteristics of forward masking data, we can have better understanding of frequency selectivity and better measurement of nonlinear input-output characteristics of the basilar membrane. For this one, it's a little bit, it touches a little bit deeper topic, but you can study in the textbook, and I'll continue. What about backward masking? Backward masking does not make sense at all, because first, the target is going on, very brief, very short target, and then after it is turned off, the masker is played. So thinking that detection of target is influenced by the masker that is coming in the future, it does not make sense, right? It does not make sense. So what's going on here? The first answer is again we are talking about very short time gap. In this case, for backward masking is even shorter than forward masking. So typically we are talking about time gap less than 10 milliseconds or just a few milliseconds. So it is very short time gap between masker and probe. As I said before, if you think about the neural characteristics that are slow, then things can happen is when you detect the short tone, and your time frame for the neural bunch of neurons to react to this short target frame can be influenced if the masker is coming almost right after, just a few milliseconds. Then there is some influence that we can expect some influence. That is a backward masking. So then it is fairly short. So typically speaking, backward masking is not really useful in terms of understanding basilar membrane or anything like that, or masking patterns, anything like that. But there's one useful thing out of backward masking. So the presumption here is that whenever we listen to a sound and process it with our brain, there is some kind of analysis time window which can be short. In other words, whenever we listen to something, our judgment, our perception does not come simultaneously, instantaneously. There may be some time gap, which may be few milliseconds or few tens of milliseconds, depending on the level of the sound. So there's this time period, time window for analysis for our perception. So that's the presumption behind this backward masking. So the practical application of backward masking is this. If someone has some compromised auditory processing capability, then this analysis time window can be longer, or longer than normal hearing listeners. And some researchers with curious minds have tried to test backward masking with some children with some auditory processing disorders. Specifically speaking, some children with a condition called specific language impairment, SLI. The results show that this population of children shows substantially longer period of analysis time window than compared to normal hearing children. Meaning that these children will require longer time window to process the sound. So this is one excellent example where a variety of psychoacoustic testing principles, testing methods can be used to diagnose some children or some people, some other listeners with some specific conditions, and we learn from this. So I hope someday in the future you will find something. You will become one of those people who find something that can be useful to use for future diagnosis in audiology.